Okay, thank you. I'm very happy to be here to participate in the 2022 Löwdin Symposium. And 2 years ago, probably all of you remember, we were doing this on Zoom from our homes. It's so much nicer to be here in person. So I would like to tell you about path integral methods and energy transfer, and in fact I'm going to focus on energy transfer in molecular systems because in 2020 I focused on methods, so I would like to make this a bit different and tell you about all the fun things that we can do with path integrals. So what is excitation energy transfer? We have molecular aggregates. We're exciting one of them or a combination of them, and we want to see how the energy gets transferred to other units. And this is an interesting problem. It's also a problem that is tough to do theoretically, very often because the molecules can be strongly coupled, because they have molecular vibrations, many molecular vibrational modes that interfere, and they can suppress quantum interference. They can change things. They can lead to vibronic effects. We're looking at non-adiabatic dynamics, really, and there can be also tunneling, zero-point energy, and phase interference can be very important. And the processes can take place in complex environments. Also, the couplings can be in the intermediate regime, can be in the same range as various timescales that we get from vibration and electronic degrees of freedom. So also there are finite temperature calculations we need to do, and there's a huge number of states. So they are challenging. If we use standard approaches, try to solve the time-dependent Schrödinger equation to study the dynamics using wave function methods, we run into the infamous dimensionality crisis of quantum mechanics. Basically, the wave function, the volume of the wave function grows exponentially with the number of particles. So what we're going to do is something different. We're going to use the path integral approach of quantum mechanics, which is physically motivated, very simple conceptually. It's basically the generalization of the two-slit experiment. We all know that. And it's the principle of quantum interference and quantum superposition. So the postulate is that the quantum mechanical amplitude is given by a sum of amplitudes along all possible paths that the particle can follow. And it is a principle of quantum interference, again, in superposition. It's exact quantum mechanics. It's exactly equivalent to the Schrödinger equation. So it includes interference, tunneling, quantum dispersion, zero-point energy, decoherence, detailed balance. Everything is in this very simple idea. Now, we also notice that all paths have the same weight. So we get enormous interference. In other words, everything comes from quantum interference in the path integral. If we try to take the idea, the path integral, and discretize the paths on a space versus time grid, you see immediately that the number of paths we get grows exponentially with the number of time steps. So even for a single particle, we have a huge problem because we very quickly reach astronomical numbers of paths, and we can't enumerate them. And of course, things get even worse when we have multiple particles, really large systems, lots of vibrational modes, and so on. At the same time, the problem in real time is that because of the interference, because we want to account for all this quantum interference exactly, we have a highly oscillatory integrand. The integrand oscillates like this, up and down, and Monte Carlo stochastic sampling methods don't work at all. They produce garbage in this case. So what can we do? Is there anything we can do in this case to use this approach? And notice also that the advantage, one advantage that you notice with the path integral is that we don't have to store wave functions. So it has the potential for calculating properties in large systems, but we have to deal with how to sum all the huge number of paths. The idea we have followed in my work for a long time is to look at the structure of the path integral and try to understand the physics and to use the physics to disentangle the variables and disentangle this huge sum. What I mean by this, to give you an example, is if I'm given a multiplication like this, and at a glance it looks like I have to do some work to do this product, But if I look a little more carefully, I see that there are 2 4s here and 2 25s here. And if I just regroup my factors, I can immediately see that this is 100 times 100. So I've done it without doing the work. So this is what I mean. We need to look at the structure and see if we can identify structures that allow us to disentangle the sum and turn it into a number of operations that we can easily handle. Over the last 30 years or so, we have started looking at how to do this. And we've gone a long way, actually. And we started by noticing that for systems coupled to dissipative baths, we can decompose the path integral, we can disentangle the variables, and turn it into an iterative procedure. I'll tell you a little about this. This is a method we call QuAPI, quasi-adiabatic propagator path integral. And this gave us linear scaling with propagation time as opposed to exponential scaling. And there were various accelerations that we noticed later on. Blip decomposition, I'm not going to tell you very much about this today. But very recently, we realized that we can further disentangle the variables by implementing other ideas that I will tell you about very quickly. And this eliminates the tensor storage of QuAPI. We have also extended this method to unharmonic environments by combining the path integral with classical trajectories. And this is a method that we call QCPI. And also we have extended it to systems that include many coupled molecules, many coupled chromophores, for instance, each with their own vibrations. So, and we do this with linear scaling. We call it the modular decomposition. So just to set the stage, here is an important class of problems, and many of these problems in energy transfer are accurately described by this Hamiltonian, called the system bath Hamiltonian. We got a system described by a coordinate S, which could be continuous or discrete, and a large number of harmonic degrees of freedom, the bath degrees of freedom, which could be molecular vibrations, and they're coupled to the system. Now, one of the very nice things, the advantages of a path integral, is that we can integrate out harmonic degrees of freedom exactly, analytically, at any temperature. And when we do this, we get what Feynman called the influence functional that contains the effects of the environment on the system. If we didn't have that, if we only had the dynamics of the system, we would get a path integral where the structure of the variables looks like this. The variables at time point 0 are coupled to the variable at time point 1. Time point 1 is coupled to time point 2, and so on. This is a consequence of the dynamics being described by the time-dependent Schrödinger equation, a first-order differential equation. But when we integrate out a bath and we have the influence functional coupled to the system, what we get is this structure, this entanglement, where all the variables are coupled together. And this is known as memory or entanglement or non-locality. And we lose the locality in time, basically, which means we can no longer propagate the dynamics one step at a time from 0 to 1, 1 to 2, and so on, because all the variables are coupled together. Now, a long time ago, we realized that this memory that comes from, if it comes from condensed phase environment, it is finite-lived. It lives a finite time. It decays to 0 as we go farther into the past. And this allowed us to decouple the variables and decompose the path integral into a series of iterative operations that involve tensors. They involve tensors, or you can think of them as arrays of paths or amplitudes along arrays of paths. And here they are, for instance. And these paths span the memory length. And then you see that I can go, because the variables couple points of one color to points of the next color, I can go iteratively by carrying this array of amplitudes along these paths. And I can iterate in time, which means I get linear scaling with propagation length. This is the exact QuAPI approach, and it has been used a lot and also has been developed further by us and by others. There's no limitation as far to that type of environment that we can use this way. Harmonic environments only, though. So most recently, we realized that we can make this even more efficient because the tensors that we need to store with QuAPI span a number of time steps, and we would get, in principle, exponential scaling with memory length. In practice, it's often much, much better in situations where we don't have to do this at all. But in general, there would be a steep scaling with memory length. And it turns out and this is an analytical result, it's not a tensor compression or anything like this, that we can further decouple the variables inside the memory length and turn the QuAPI algorithm into an algorithm that involves only small matrices of size equal to the reduced density matrix of a system. In other words, if I have a system with n states, these are n squared by n squared matrices, which is something very small. So this is, again, exact and analytically derived. By doing this, we're able to get rid of tensors, no tensor storage whatsoever, so we can now go to really large systems and converge calculations, even if there's very long memory, and I'm going to show you examples of this. Another, an extension of all this to systems in anharmonic environments, such as solvents and protein environments, involves combination of the path integral with classical trajectories. And we call this method QCPI. It is a rigorous quantum classical approach. It does not rely on Ehrenfest forces or anything like this. And it is rigorous because we are combining quantum and classical methods here, but in a formulation that is local in space. The path integral, unlike wave function, the wave function formulation, is local one path at a time, because a path is like a trajectory. So by combining a path of the system with a classical trajectory, we're able to account for their interaction between the system and the particle of the environment exactly, and include all their phases without any approximation. And if we look at the structure of the expression, what we get is this huge path sum again that we had before, and in addition we get a phase space average over initial conditions of the trajectories here of the environment. So we have to evaluate this, and of course it looks like we have a huge number of paths because again the number of paths grows with time. And we can still decouple the variables in ways that are analogous to what I showed you before. They're a bit different here because we have classical trajectories, we don't have an influence functional, but we can again take into account, exploit the ideas of the coherence and decouple the variables, and we can turn this into an iterative procedure. So this works for systems in complex environments, and you can see here everything is given by phase interference in this expression. There is nothing. All the decoherence comes from these phases of the system coupled with its environment. And here, last, for methods, the modular path integral. It's a method for handling large aggregates or arrays of spins, where we have each unit is interacting with its own bath of vibrational modes, and we have many, many units coupled in a one-dimensional topology. And what we do in this case is we write the path integral, and we connect the variables, we evaluate it along the dimension of the direction of the aggregate. So we get linear scaling with a number of units. Again, I'm not going to tell you many details here, much detail, because I have talked about these methods before, and I would like to tell you now how we apply these to learn the intricate details of energy transfer in molecular aggregates. So let me start with the dynamics of a dimer. And really, when we're discussing energy transfer in molecular aggregates, again, it's a problem in non-adiabatic dynamics. So I'm going to take a dimer, and I will call the molecules A and B. And I can place the excitation on A, or I can place it on B. I'm going to look at the single excitation subspace, and here it is. This is the configuration. The first configuration, it's 1A, 0B. This means A is in state 1, the excited state, and B is in the ground state. And I can transfer the excitation to the other molecule. I can have 0A, 1B. All right, so I have these two states. Now, if I take a molecular vibration on molecule A and another molecular vibration on molecule A, take two of these, and look at these potential surfaces, what I get is the configuration 0A, 1B has both modes in the ground state, so it's here, but the configuration 1A, 0B has both modes of A excited. So it's going to be displaced along both directions here on this axis. On the other hand, if I take a vibrational mode on A and one on B, like here, then I get this structure. Here's the ground state, and here's the first excited state, 1A, 0B, and here's the other excited state. So you get these pictures just to understand what we're dealing with. And it turns out that you have a homodimer, and I look at vibrational modes that are identical on the same frequency, the same mode on the two molecules, then these potential surfaces become circular, and then you can do a transformation to the correlated and anticorrelated modes, and you can see that only the anticorrelated mode couples, and so on. This is something you can do on the dimer, and it's just nice to do this to understand things a little bit better, but in the end, in the calculations, we're not going to be using this very much because we are going to be interested in really large systems where the transformation is only limited to the dimer, just to give us an idea. Now, we're going to place the density in the Franck-Condon region initially here. So we're going to bring it up from the ground state up here, and it's going to start moving this way, and also it's going to start moving this way because we have A excited, and it's going to start going back and forth. At the same time, it's going to be leaking to the other potential surface because the states are coupled, and we're going to see how things are going to evolve. So I'm going to start by taking two vibrational modes that are weakly coupled, and lots of modes like this in molecules, weakly coupled to the system, to the electronic states, and I'm going to watch the electronic vibrational density. I will call this EVD. It's the correlated electronic and vibrational density, or the density on the two excited states. And it turns out that the vibrational density under these conditions, weak coupling and low temperature, remains compact during the dynamics and Gaussian-like, and you can see it here on the left. If I plot the average position, since I have a Gaussian-like function, the average position gives me a very good approximation the location of the peak of the density. So I'm going to look at the peak of the density as it moves, and you see if I plot it here, it does something pretty weird here. This is the density on one of the excited states in red, the other one is in blue, and you see it almost looks like oscillations, but it shoots up here very far. And the reason for this is that as the density moves here, this is my picture of the two diabatic potential surfaces, I'm putting it here and starts moving to the right, but at the same time as it moves toward the right, it leaks to the other state. So the right potential surface is depleted. And if I take a big chunk out of a Gaussian, I leave very little density there. And when you do this, it appears that the peak is moving far to the right. So the peak of the density moves far beyond the classical turning point, and we're going to see the average position shoot up. That's what it does here. Now, when I take all the other modes and couple them and include them, this effect goes away. We get a lot of smearing, and then the peak position looks nice oscillatory like this. It looks like these oscillations are very regular on the two states. It looks like they live forever. They don't live forever. They eventually decay. You can see here a much longer time. You can see the amplitude going down. And they decay because even though these are normal modes that are not coupled to each other, they're coupled through the system indirectly. So they exchange energy. The vibrational modes exchange energy by coupling to the electronic states, and this is how eventually they equilibrate, and everything equilibrates, and everything is nice and gives us the right thermodynamic limit. If I now look at two vibrational modes under the same conditions and follow the peak of the density in 2 dimensions, I get these kinds of pictures. And if you ignore the yellow stuff here, this is color-coded based on the density on that potential surface. And if you ignore the yellow stuff, which is very low density, what I get is these pictures that look like Lissajous pictures, and some of you may recognize these as pictures of classical trajectories in classical dynamics in the regular regime that is observed in systems that are not strongly coupled in classical systems. And they have all kinds of interesting shapes, and it looks like then that the trajectories that we get, they're not trajectories in the calculation, right? But I'm talking about the trajectory of the density peak. The trajectory follows regular light dynamics. When I include all the other modes, again, they smooth out these pictures, and all of these pictures, they all look differently, look like pretzels or butterflies and so on. They all become simple and rectangular, and they shrink to this. So this is the picture with weak coupling and low temperature. And if I now go to modes that are strongly coupled and or at high temperature, things get very different. Now the density is no longer Gaussian. It does all kinds of interesting things, quantum interference and wiggles here, all kinds of things. The energy exchange is faster, and the modes equilibrate much faster. And now the density moves far away from the crossing region. And when this happens, we get density retention. When it moves far away from the crossing region, then it stops transferring at some times, and we get density retention, which means that we can get the population to kind of stabilize temporarily in the dynamics. And these are the two-dimensional analogs of this. You see, now we no longer get these simple regular dynamics pictures, but we get something much more entangled here, much more complicated, and this is chaotic motion, basically. This is the signature of chaotic motion in classical systems, as we see it now in the quantum systems. So let's get to excitation energy transfer in molecules. So I'm going to look at aggregates, such as J aggregates, for instance, stacked molecules, and specifically of perylene bisimide. And also we're going to talk about light harvesting systems. I'm going to start with the Frenkel exciton Hamiltonian, where I have the single excitation subspace. The electronic states are coupled, and one unit of excitation is allowed on the whole complex. Each of the units is a molecule and has its own vibrational degrees of freedom that I call Q, and it has a ground state and an excited state, which are displaced. So the equilibrium geometry of the ground state and the excited state are different places, and that's how we get these shifted parabolas. So we're going to be treating this whole thing exactly by path-integral methods, no approximation given the Hamiltonian. So let me start with PBI. So I have PBI is this molecule, perylene bisimide. Here it's of interest as a promising candidate for energy transfer. And it has an interesting vibrational spectrum. This is from calculations, actually, that we got from Oliver Kuhn's group in Germany. And it has two strongly coupled modes, vibronic modes. Here we call it Q25 and Q27. And for reference, this is the exciton splitting of the electronic states of the system. So when we look at the dynamics of a dimer, what we get is the population. Here I'm plotting the population of the excited state, and it starts here at 1, and it has this, shows this wiggle here, then goes down, and interestingly what you see is the temperature dependence at this point, these are different temperatures, is quite strong, but at this point we get no temperature dependence. So what are we actually seeing here? I'm going to show you pictures of the electronic vibrational density again, and this is for the dimer. And this is on the left here, I have just two modes, and I'm showing you the density as a function of these two modes. And you see that these modes are strongly coupled, so the density is not Gaussian at all. In fact, it develops interesting structures and even internal holes. So we can see the density here in this picture, projection of the density. It moves out to the turning point, and that's what we call depletion. This depletion means things kind of stall temporarily because because population stops transferring when the density moves far from the crossing region. If I look at the dynamics of this vibronic mode alone, it's this. So it shows this shoulder here. It's this effect that the density stops transferring, then resumes, and so on. And when I look at the dynamics with all the modes together, you see that this leaves a signature on the other. On the dynamics of the overall dynamics, but there are other effects as well. In fact, the effect of all the other modes is to change this part of the diagram, of the picture here, and show us temperature dependence. And once we go to longer times, things change very much. And here's the density again for another set of two modes. And you see now here, you see the two modes alone, and the two modes in the presence of all the other modes, and you see that the other modes, again, have a blurring effect, and they turn to smooth out those densities and make them simpler shapes. And here's actually, I have a quick video of this, so you can see the density. See if I can play it like this here. Okay, this didn't, what happened here? Okay, let's skip the video. All right, I don't know why. All right, so now I'm going to go to long aggregates. So this is an aggregate of 25 units. And on the left, we see the dynamics, the populations of all the other states. We are placing excitation on the edge unit, and we see all the other units get excited one by one in sequence here in the absence of vibrations. And we have pretty simple shapes in the absence of vibrations here. And when we add vibrations, the vibrational modes, then we get again, the shoulder here coming from vibronic mode, and as we go to longer times, we get smoothing and a lengthening of the time scale for transfer, and these curves look much more dull as opposed to being sharply peaked. And similar pictures when we excite the central unit. And if we take snapshots of the density, what we see is in the absence of vibration, we see a lot of holes. That's because there is quantum interference, really full-blown quantum interference, and we get oscillatory structures. But when we average over all the other vibrational modes, we get much more compact and smooth densities. So the temperature effect, again, here is very pronounced at longer times. This is the second dip here. And unlike the dimer, the populations go to zero quickly. They don't recur very much. So what is contributing to what here? We can do an analysis by grouping the vibrational modes into three groups, the low frequencies, intermediate frequencies, and high frequencies, and we can see what contributes to what. And what we see is that, of course, one would expect that at short times, the high frequencies contribute. Of course, we find this, but we also find that the intermediate frequencies and low frequencies contribute quite significantly at times that are shorter than I would have thought, at least. And so once you go after 20 femtoseconds here at this time, you get significant contributions from the other frequencies. And they all have this blurring effect, again, dissipative effect, that they smooth out the populations. And in the end, when you look at all these pictures, there's quite a bit of complexity here to see in the dynamics coming from a large number of modes. And last, I'm going to move to the excitation energy transfer in light harvesting. This is one of my favorite systems. This is nature's light harvesting, energy harvesting apparatus, and it has very interesting physics as well. So we're going to look at the LH2 complex, light harvesting complex 2 of photosynthetic bacteria. That looks like this. Here there are two different views here, and here is the complex without the protein, without the rest, and the carotenoids, just the chromophores here. It is composed of two rings, the outer ring, known as B800, and the inner ring, known as B850. And in this particular bacterium, the outer ring has 8 chlorophyll molecules, bacterial chlorophyll molecules, and the inner one has 16. So we have a total of 24 molecules here, each with their excited state and ground state, and each of them is coupled to 50 molecular vibrations. Now, why 50? This is determined here, the molecular vibrations that are important, are determined from spectroscopic experiments, and these are the Huang-Rees factors of the bacterial chlorophyll molecule that are obtained from fluorescence experiment again, and they determine that 50 of them are important. So we're including all of them. We don't want to leave anything out. And also, if you look at this picture here, the Huang-Rees factors, they're spread out over the entire frequency range. They're quite a bit different from the spectrum of PBI that I was showing you before. Lots of weakly coupled modes and strongly coupled modes everywhere. Let me start with the dynamics of the inner ring, the B850 ring. If I excite a unit there, one of the molecules there, I'm going to watch the energy go around. And one of the big questions here in this system has to do with quantum coherence. Does energy transfer rely on quantum coherence? So we did a study where we took chains of different lengths, and we examined the extent of quantum coherence in the dynamics. Starting with the dimer, this is a dimer of bacterial chlorophyll molecules. We see, if I plot the population, when I excite one of them, I plot the population of the excited state, and it oscillates like this. So we see quite a bit of coherence. If I had no coupling to vibrations, the curve would go all the way from 0 to 1. Right? So we get some suppression of coherence because of coupling to vibrations, but we don't get too much suppression because we still see oscillations. Now we're going to increase the length. And if I'm going to show you results for chains of 5 bacterial chlorophylls, 9 and 18, and also the B850 ring. In the absence of vibrations, again, we get these kinds of patterns, smooth curves, they're combinations of cosines. And you see recurrences here occurring. The recurrences are shifted to longer times as we go to longer chains, because the energy takes a longer time to get to the edge and transfer back. So we see that effect. Now, this is going to be retained to some extent when I add vibrations, but the coupling to vibrations is going to smear the electronic energy transfer and is going to make everything smoother, and it's going to suppress the coherence. So here's what we get. We now find that the first recurrence peak here in the pentamer is suppressed from having amplitude equal to 1 to about 0.4, major suppression. And when we go to the longer chains, we get more and more suppression. And here is the longest chain that has length equal to 18. This is another LH2 system that has 18 molecules here. It doesn't really matter. So we get a very little, this very little shoulder here. That's the only remnant of coherence that we get. If you see this in the two-dimensional picture here, this is the monomer number and this is time. You see a little bit of oscillatory motion there, wave motion, and this is the extent of coherence we have left. So coherence is certainly not completely damped, but it's not very strong here in these systems. It's at the 0.1 level, and this is damped by the vibrations of the molecules only. If I were to take the molecules, take the B850 ring and stick it in the protein environment, which we have not done here in this one, we would see even more suppression of coherence. So this is borderline, and you can start analyzing why this is and speculating why this is. So probably this is beneficial to the energy transfer in the whole complex. So let's look at the energy transfer of the whole complex now. So now I'm going to look at the entire LH2 system, the 2 rings, with 8 and 16 bacterial chlorophyll molecules. And we're going to try to understand why and how the energy gets transferred, and how does it get transferred so efficiently. Because we know from experiments that the quantum yield of the energy harvesting, solar energy harvesting, is very high in photosynthetic systems. How does it work? And before I go into the details, let me just show you this. When we submitted the first paper on this, the reviewers asked, how can you possibly converge this? All right, so here's what we are dealing with here. We've got 24 molecules with 24 excited states. Each of them is coupled to 50 vibrational modes, and also in this case, we included a coupling to a background that comes from the protein vibrations, the overall protein vibrations and solvent. So here's the spectral density. And those of you who do dynamics know that when we have a lot of peaks in the spectral density, we get a very long memory. And we have a lot of peaks here. And here is the memory kernel. And this time scale here is 1.5 picosecond. The memory lasts 1.5 picoseconds. The pathnical time step is about 7 femtoseconds, right? So we have huge memory and a large number of states. And yet, we're able to converge these calculations. And you can see convergence curves here. We're converging to a sub% level. All right? So these are very accurate results that I'm showing you here. So this is a very interesting system, and it is actually puzzling how it works, and I'll tell you why it's puzzling. First of all, we have a system that has 24 identical molecules, 24 identical chlorophylls. Yet I excite one of them, and the energy goes to the B850, the inner ring, and distributes there. Why does it do this? And you will see that this is even more puzzling when I consider various subsystems and I ask certain specific questions. So let me start with this. I'm going to take, here are the 2 rings, and here's our numbering. We start here numbering the inner ring, 1, 2, 3, and so on, up to 16, and then the outer ring, 17, up to 24. Okay? So I'm going to excite, this is what happens in nature, the outer ring gets excited. I'm going to excite a bacterial chlorophyll on the outer ring, this one, number 17, and ask and see where the energy could go. Where could it go? It could go to one of these in the inner ring, say number 3. It could transfer to 18 and 24, its neighbors on the outer ring, right? These are the kinds of things we do early on, and then could proceed from there. So let's take these subsystems. So I'm going to take the subsystem here that I call dimer A, which is number 17 with number 3, outer and inner rings, and then I'll take this one, 17 and 18, and see what they do. So dimer A is up here. These are identical chlorophylls. I put the energy in this one. Soon, quickly, the energy gets distributed between the two, as it should. 50-50 populations here on the two. And the time scale is about, what, like a picosecond or half a picosecond for the lifetime. Okay, that's what we get. If I look at these two, 17 and 18, I get again similar pictures because these are again two identical chlorophyll molecules. But they're not as strongly coupled, so it takes longer time to transfer. All of this makes a lot of sense. And in gray here, you see the curves that I would get in the absence of vibrations. The transfer would be 160 femtoseconds here in the absence of vibrations. So we'll take this and now go to the entire B800 ring, the outside ring, and see what happens. And I already showed you what happens when I look at the inner ring. So if I look at the B800 ring, the energy of the initially excited state, here, number 17, goes down, and then shortly after that, other populations rise. Number 18 rises first, as we might expect, and 24, they're identical, right? So this rises here, and then the next one rises, 19 rises, and so on. Okay, that makes sense as well. So we see the time scales here, and we see what happens. Now, let's look at these and compare. Now, what I'm going to notice here is two different observations. One is in red, one is in green. Let's look at this one. So in the absence of vibrations, the energy goes to bacterial chlorophyll number 3 in 160 femtoseconds. That's what I see from this. In the absence of vibrations, right? This very rapid decay here. Okay, so it goes from 17 to 3. Very quickly. So now I'm going to put to look at the whole complex, the two rings together, and see what we get. In the absence of vibrations first. In the absence of vibrations, what I get here is these pictures. So here's the initially excited state, goes down, and then other states rise. Which ones rise? The ones of the outer ring only. The inner ring populations are down here, a few percent. They don't rise. So the energy circulates on the outer ring only. And here are snapshots. You can see here these pictures. Here's the inner ring. These are the 16 units, and here are the outer units. And you can see the density contours here. I start here, and quickly it spreads a little bit on the inner ring and then on the outer ring, but mainly, after a long time, mainly the energy resides on the outer ring. So it no longer goes to the inner ring, even though that's where it would go first if we only looked at dimer A. Okay, so that's the first puzzle. The second puzzle is, go back, the one on the in green. Now, when vibrations are included, the energy is transferred to chlorophyll 3 and to 18. One to the inner ring, its nearest neighbor on the inner ring, and its nearest neighbor on the outer ring, right? Let's see what happens when I have the whole complex with vibrations here. Now, you see that the energy goes only to the inner ring. And here the density contours, it starts moving to the inner ring, very little density other side, very quickly, in 200 femtoseconds, it is populating the inner ring. And very little on the outer ring. So when the whole thing is together, it doesn't work as we thought it would work. Why is this? Well, this is because in the composite complex, what we have is an energy gradient that we get. And that's because the chlorophyll units of the inner ring are strongly coupled together. When states are strongly coupled together, they split apart. They split apart and they lower the energy. So the strong coupling of the inner ring lowers the energy of the chlorophylls on the inner ring. So all of a sudden, when we're looking at two chlorophyll molecules, one on the outer ring, one on the inner ring, they're not degenerate in energy anymore. The one on the inner ring is lower, which is good for thermodynamics because it means it's going to trap the energy. But it is not good for kinetics because when we have states that are very different in energy, population is not going to transfer. In an asymmetric two-level system, you don't get transfer of population unless you couple it to something else. So the only way the energy is going to be transferred is by coupling to vibrations. And that's exactly what we see. So when we look at population curves with vibration, including coupling to vibrations, now we see that the populations of chlorophyll units on the inner ring, they do rise. There are many of them. They don't seem to rise much because there are many of them. Okay, the total rises a lot, though. This dashed green curve here. This is the total population of the inner ring, and you see it goes to 0.9. So it transfers 90% of the population to the inner ring now. And that's, again, the combined effect of the tight structure of the inner ring, which provides the thermodynamic bias, and the kinetic effect that we get from coupling to vibrations. All right, so this, we understand what's going on here and how this works. So one more point I want to make here is that if I were to treat the nuclei classically and not allow them to be quantum mechanical degrees of freedom that have vacuum fluctuations and 0-point energy and everything else, I would not get this quantum yield. I would only get 2/3 of the energy to go to the inner ring. And that's what you see here in this curve in yellow, and you don't get the high efficiency anymore. So it's also the quantum mechanical effects of the nuclei that give rise to this. And very last, I'm going to ask the question, what happens if I excite an eigenstate of the B800 ring, because that's what happens, probably, if you have a symmetric system without strong fluctuations anyway. And what I have here is the eigenstate structure of the electronic, just the electronic states, 24 of them. And the electronic states are split into two bands, the B850 band, which are the low-lying states and the high-lying states, and the B800 band that's in the middle. And this one is in the middle because the chlorophyll units of the B800 ring are not strongly coupled, so they're not split very much. So these states sit in the middle. Interestingly, though, there are two states, number 10 and number 13, that have mixed character, have populations on both the inner and the outer ring. And these play an interesting role. So we're going to look at relaxation of excitation energy. And what we have here is the populations. I am exciting here an eigenstate of the B800 ring, number 12, for instance, right here in the middle of this band. And what we see is these population curves. So we see a very rapid decay and then a very slow decay. And we see this picture in almost all cases. So we have a very rapid time scale, about 70 femtoseconds, and then the populations of the lower eigenstates rise slowly, first sharply, and then slowly equilibrate, and the whole thing equilibrates after about 1 picosecond, and this is an excellent agreement with experiment. So interestingly, though, if you look carefully, what you see is that these population curves do not follow the cascade of energy states. So where I'm starting here, I should go down one at a time, populating these, but actually there are anomalies. They don't follow in sequence. Another interesting effect is that when I look at the when I populate, what happened here? There. When I excite a different state, I excite one of these mixed states. What I get is I completely, okay, I lost it, sorry. There we go. I completely lose the fast time scale, and now the equilibration happens very rapidly. in this case. So that's when I excite these mixed character states. Also notice that regardless of what state I excite, the total population follows a perfect exponential curve. Here's the log scale. So why is this? Why are these anomalies observed? It turns out that if I look at the populations at equilibrium and plot them on a log scale, in the absence of vibrations, I get a monotonic dependence on the quantum number because the Boltzmann factor is monotonic, decreases monotonically with energy. But when I include vibrations, I see these anomalies. I see a little bump here, another bump there. It looks like thermodynamics is not being followed, right? Something is inverted. And we have an inversion of energy levels, that appears effective energy levels, which is caused by the vibrations. The vibration dressed states are actually inverted in energy, and the vibrations push those mixed character states all the way down outside of the band, of the B800 band, and that's why they get populated later in this case. So this is all I wanted to tell you about. So lots of interesting dynamics here that you can uncover using pathological methods, and lots of very interesting systems here to study. And I would like to acknowledge my co-workers. I already mentioned on several slides. Most of the work on energy transfer was done by an excellent graduate student, Shohan Kundu. And most of the funding over the years has been provided by the National Science Foundation. I would like to thank you again.
Thank you, Nancy, for a very nice presentation. Very interesting results. I guess we have time for a few questions. Do we have any questions from the audience? We have one up there. I see.
Thank you very much. I wanted to ask how sensitive are the results to the structure of the complex? So how do you prepare the complex and the distances? Is it entirely symmetric? So all units identical, if I understand correctly here, and how much does it change if you sort of take into account the disorder?
Yeah, okay, great question. So first of all, I did not mention, I think it was on the slide, but the parameters, the electronic structure was done by Scholl-Mokommel's group. And we use also electronic couplings. We don't include dynamic disorder. We include dynamic disorder. We don't include static disorder here, and that is something we could do. We have done this for dimers only, and we see additional. There's additional damping basically once you include static disorder. But this is something we have not done. So we would expect more damping of coherence. The effects of population transfer, timescales, and so on don't really change very much.
Do we have any more questions? This ring behavior that you see there, is this something that you would predict for a solid as well? It looks almost like a solid behavior when you have this. If you have a nanoparticle, for example, a solid particle with molecules on top, and you see a discharge transfer, this energy transfer, is this a similar pattern that you would expect for a solid, or? Where you have a band structure.
In fact, these when you have a lot of states, they do form a band structure. Yes, absolutely, yes. There are all kinds of effects, and different molecules I did not talk about that also show different these kinds of effects. Yes.
Oh, that's interesting. So then we change microphone here. We thank Nancy once again. Thanks for.